is the basic one we deal with, which is our linear function. This should have been pretty straightforward. We have y equals x. Plug in -2, what do we get? -2, and then what? Wow, you guys talk. Great job. Great job. All right, so here we go. And why it's continuous? Because any x value I put in, I will get a corresponding y value. Doesn't matter what it is, okay? What is my domain? Check.
-.
Good. All right, what is my range? Yep. Yep, go ahead. Yes. Okay. Now, one thing that people have asked too, intervals of continuity, okay? The whole idea here with intervals of continuity, they only use parentheses, okay? And you do not, your pencil does not want to leave the paper. If it does, then there's going to be a split, right? So here, what would be an interval of continuity? Yeah, David. -infinity to infinity. So in this case, it's the same as the domain, okay? Where it changes, for example, is if I had something like this. The domain will read -infinity to infinity, but intervals of continuity will break at this value, okay? Yes? Intervals of continuity always in parentheses, okay? Anytime, and Campbell, thank you for bringing that up. Anytime it says interval, okay, interval of increasing, interval of decreasing, interval of positive and negative, we use parentheses, okay? Great question. Where are we increasing? Eleanor. Good. Okay. And this graph is not decreasing, all right? So that's our linear function. Then we move on to quadratics, okay, which we have seen before, all right? So we have -2 squared, and you guys know this already, but just to show, -2 squared, what do we get? Anybody, go ahead. Then what? Awesome. Okay, so when we graph, okay, quadratic function is our U shape, okay? What is our domain? David. -infinity to infinity. Good. What is our range? Jax?
Bracket 0 and infinity.
Awesome. What is our intervals of continuity? Charlie. Good. Mm-hmm. Right. So exactly. But that would be also the same with domain too. Okay. Yeah.
When if an interval of continuity, if you have a split, would you still put what the u?
Yes. Always. Okay. Where am I increasing? Yes. Good. Where would I be decreasing? Yeah, Noelle. Good. Awesome. And again, parentheses. What's another thing with quadratics? There's another term that we could associate with quadratics. Yep. All real numbers represents the domain. What else? Yeah. Not exponential. Not exponential. That's another function. Okay. What else? What is a term for the lowest point on a quadratic? Or the highest point? Yeah. The vertex. Okay. The vertex on a quadratic, okay, starts with 0, 0. But the vertex is always the lowest turning point or the highest turning point, okay? And there's only one in a quadratic. So one thing to keep in mind with a quadratic, if I was to split this paper in half and fold it, I would have the same y values on either side. Okay, so it's symmetrical. So what we could have done is found out these two values and automatically know that they're here. So if you find the vertex first, then you will know 2 below. Okay, you figure it out algebraically, and then you will know 2 above. Okay, because it's the same distance, it's symmetrical on either side. All right, yes?
How do you know when a line is, how do you know when something is not, like, continuing? Like,
If there's a restricted domain, if it tells you that.
like what,
Like if it says linear function from -2 to 4. Okay, yes? Yep. Yes. 0, 4 would be the vertex, yes. Okay. The next function we will see is the cubic function. Okay. Cubic function is another one we will be dealing with. So we have -2 cubed, -1 cubed, 0 cubed. Okay, and remember when you're cubing something, it's -2 times -2 times -2, not -2 times 3. Okay, so -2 cubed, what do we get, David? -8, -1, 0, 1.
8.
Good. Okay. And this is the same thing too. If I plug in an x value, I will get certain y value. So what is my domain? Ryder, what's my domain? Good. Tommy, what's my range? Careful. -infinity to infinity. What is my interval of continuity? Campbell. Perfect. -infinity to infinity. Because you do not lift pencil. Jaden, where am I increasing? Good. Okay. So this type of graph, okay, we have seen actually before, all right, and some of the homeworks in terms of increasing or decreasing. This point right here, which we're going to learn about a little bit later, is an inflection point, okay? That's an inflection point where it looks like it is flattening out, but it doesn't, okay? It's a constant increase, all right? What do these domain, range, interval, continuity increasing also resemble that we've seen already today? What is it very similar to? Yes.
A quadratic.
Careful.
A quadratic.
Okay, a linear function. This is very similar to a linear function, okay? Think of it this way. Linear functions have an exponent of 1. Cubics have an exponent of 3. Those are odd exponents, so they're going in the opposite directions, okay? They're linear functions continuous, all right? The next one is a square root function, okay? Square root. Why didn't I include negative values? Eleanor. Good. A negative value will give you an imaginary solution. So, what is the square root of 0? Square root of 1. Square root of 4. And if I added 9, 3. Good. Start here. Okay. Yes. You can't, because if you're just substituting in, you're not taking the square root of either side. And if we plugged in -1, we would get an imaginary solution. So this part will not exist. All right. What is my domain? Kip, what's my domain? Perfect. Perfect. Good. Let's see. Kaden, what is my range? Good. Awesome. Okay, let's see. Nick, what is my interval of continuity? Good. And again, it doesn't matter if it's open or closed. We're only using parentheses. Okay. Where am I increasing? James. Good. Awesome. Good job. All right. And the last one is our absolute value function. Yep.
For square root one, why was it not like on the left side?
So we can't have negative x values. Okay. Negative x values will make it imaginary. All right. Or not real solutions. So absolute value. Absolute value of -2. -1. 0. 1. 2. 2. So no matter what, if there's a negative inside the absolute value after you're evaluating, it ends up positive. If there's a positive, remains positive. Okay? All right. Let's see. Kaylin, what's my domain? Good. Awesome. -infinity to infinity. Pearson, what's my range? Perfect. Good. Christian, what's my interval of continuity? Good. Where am I increasing? Catherine. Good. And where am I decreasing? Kate. Good. Awesome. Okay. Now this one here, what does it resemble? What do we think? Yeah. It's a V shape. Okay. It is a V shape, so absolute value V. Good. What are they similar to? Campbell. A quadratic function. It's very similar to a quadratic. So what other term can we use here? Yep. The vertex. Again, the vertex. Awesome. Okay. Awesome. So these five functions. These five functions are called our parent functions. That's another term we use. Okay, these five functions are called our parent functions. Okay, these are what we're always referring back to start before we transform. Okay, so this first one, we have a linear function, then we have g of x equals x plus 5. What are my new g of x values? Charlie?
4, 5, 6.
Okay, so if I go ahead and plot those, I know sometimes they'll be off the graph. So, all right, so those are our new values. What do you notice? Jax?
Well, I just thought of it. Aren't they parallel?
Okay.
Well, they also have different equations.
They are different equations. You're right. Yeah.
I think they also have linear. Isn't it called like a linear? They also linear function.
They are linear functions. Good. Jaden? G of x is 5 units. above f of x. Okay, good. What else? What else do you notice? Yeah, David. Slopes are the same. Good. Okay. If I had to tell the difference between f of x values and g of x values, what would you do? Add, subtract, multiply, divide. Charlie?
GX has point, higher y-intercept.
Higher y-intercept. Good. So we go from f of x has 0, 0, and g of x 0, 5 for y-intercept. Okay. If we look at our current f of x values, what operation will we need to use to get to g of x? Yeah. Okay. Add 5 to f of x values. Okay, great. Okay, so having that plus 5, we moved up, right? So we increased our original y values by adding 5. Okay. Now we're going to look at the quadratic. Okay. What are my g of x values? Yeah, Kate. Good. Okay. So 2, 6 here. Okay, so according to my table of values, this is what I see. But with quadratics, and we know it's a quadratic because of a squared term, okay? That's how we know it's a quadratic. What other value can we fill in here? What other points to make it the full U shape? Yes. Yep.
For GX, do I think you would try to duplicate it on the right side, like the same point of the opposite, so that you could do like, well, actually, no, that wouldn't work because it's not in the center.
Okay. Okay. Campbell? X equals 3. What would my y be? 1. Good. And then I would have 4, 6 as well. So this would be if I could add more points. Excellent job. If I could add more points to see a full quadratic, if I'm still using the table of values, because something happened to the graph, I only see part of it. But knowing a quadratic is symmetrical, I could go through the middle and match up the points by distance. Okay? So what did you notice happened to this graph? What are some changes from our parent function, which is x squared, to x minus 1 squared minus 3? 8. Okay, what is the vertex? Good. So our vertex is 1, negative 3. Excellent. It's the lowest turning point. Okay, so if I know my vertex is 1, negative 3, how did it move to get there? What direction? What happened? How did I go from 0, 0 to 1, negative 3? What are some movements this graph made? Okay. Good. So right 1 and down 3. So you look at your original equation, okay, and the purple is my transformed equation. Well, I had to go down 3 into the right 1, okay, and that starts my new vertex. But all of the points also moved right 1 and down 3, okay? So one thing with quadratics, once you establish where the vertex is, we could have just found out those 2 points, negative 1 and 0, and then we would have found out 2 and 3 because these are the same. Okay? Those are the same. So when we get into graphing these types of functions, We will start with the parent function, and then we will transform them. Okay? So if you could take out your Chromebooks or laptops right now, okay, and keep your notes out, but turn to the next page where you see this box. Okay, turn to the next page where you see this box. Okay, so if I go to Google and type in Desmos.com, okay, Desmos.com, this is what you will see. And then you want to click Graphing Calculator. Okay, so Desmos.com, and then the Graphing Calculator. Okay, so in this first box, if you notice there's a keyboard at the bottom, just click it up. And we're going to put our parent function in first, which is x squared. Okay? Our parent function is x squared. We are going to be putting in some values to show or discover how this graph changes. So, if you notice on your notes in that box, there's this equation. Okay? That's the x squared equation. However, if there's a number in front of x squared, something happens. If there's a number inside parentheses, something happens. If there's a number outside, something happens. So we're going to start with the number in front, which is A. A, H, and K, you need to know from now until the end of the year. Okay? Those three letters, A, H, and K, will be with you forever. Okay? So, an A value means a number in front of x squared. So what I want you to do is you could do a bunch of different graphs. Okay? Just click enter every time you change it. All right? What I want you to do is choose any number, put it in front of x squared. So put a number in, x squared, see how your graph changes. Do multiple of them, all different types of A values that it could be. It could be negative, it could be fraction, it could be whole numbers, whatever you want. I want you to see if you notice any changes. There it is. It's getting closer and closer and closer to the y-axis, right? How else can we describe it? Yeah, James. Okay. With quadratics, you can't really use the slope, okay, because it changes, but you are correct. It's getting steeper, right? Okay. So if your A value is greater than 1, and we'll use Grant's example, so in the box in your notes, where it says A equals, we're going to have a few different things here. If A is greater than 1, this graph became narrower, meaning it's getting closer and closer to the y-axis. Okay? It's also called a vertical stretch. Okay? So if I inputted, and I'll just show you what Grant had as well. Okay? My original graph, my parent function, was red. But if I put a positive value in front of x squared, it's getting steeper and steeper. It's narrow. What other A values did you put in? What are some other examples that you chose? Eleanor. 0.5. Okay. So if I did 0.5 x squared, what do you notice? How many of you did a fraction of some sort? 1/2, 1/3, 3/4. Okay. What did we notice? Yeah, Catherine. It got wider. Excellent. So y equals 1/2 x squared. It became wider. Okay. This is also called a vertical compression, or some might say a shrink. Okay, it's getting wider. It's a vertical compression. So this could be any fraction. However, if you have a fraction 5 over 4, 5 over 4 is greater than 1. So therefore, it will be a vertical stretch. So this number has to be between 0 and 1. Okay? So it's a fraction. Yes.
What if you did 0? Like, trying to do 0 maybe like.
Because 0 times anything is what? 0. So it would just be a line. Okay. Is there anything else you put? Anything else? Yeah.
What if someone put a fraction? Does that change it at all, or
The fraction we just went over.
it's just the same as the decimal, right?
Yep. Anything else? Yeah. -4. Okay, I'm glad you brought that up too. Okay, -4. There's two things going on here. What's one thing you notice that is different from the rest? Yeah. It's upside down. So if we have an a value that is less than 0, meaning it's negative, so y equals -x squared. Okay, this is a reflection over the x-axis, meaning the graph opens down, okay, meaning it's pointing down to the up. So the negative only means a reflection, but there's a 4 also in front, so what else is happening? Yeah, Charlie. There is a vertical stretch. So in that case, thank you for saying it. In that case, -4x, the negative only means reflection. The 4 means a vertical stretch. So when you see that a value, you want to take the absolute value to determine if it's a stretch or shrink. The negative only means reflection. Okay? Questions? Okay. So now, we're going to see what happens with the h value. Okay? So you could leave your parent function. I'm going to go ahead and delete these guys. Okay? Now, you're not putting an a value. You're putting something for h. So y equals, with parentheses, x minus the number squared, in parentheses, x plus the number squared. See if you can figure out what's happening. So I'll put an example up here. I'll wait to do that. When you're moving left or right, if it's x plus h squared, it's moving to the left. If it's x minus h squared, you're moving to the right. Okay? Left or right changes your x values. Okay? Left or right changes your x values. Okay? Left or right. It's opposite of what you see. Okay, so we did a so far, which changes the shape. And for our a, did it change our x or y values? What do we think? Eleanor? Y. Good. Okay. Our h values change the x. Which one haven't we done yet? What type of transformation or movement haven't we done? Yep, Grant. The what? When the vertex moves. So what? Yeah. Not rotation. Careful. What do we think? How else would the vertex change if we're not moving left or right? up or down. So, what color haven't I used yet? X values left to right. Okay. So the next I want you to do, you're just going to have x squared and then the plus k. Bless you. Plus k. X squared and plus some number or minus some number. Okay. What do we notice? Yeah, Kayla. Good. So if we have x squared plus k, it moves up. If we have x squared minus k, what happens? Down. Good. And what does this affect? What values? Y. Good. Changes y. Okay. So going through this information we just did, I'm going to put an equation on the board. And I didn't do this in my other two classes, but if I had who could tell me, using some of the lingo we just did there, with my purple graph, what happened? What's one change? Jaden. Down 2. What's another? Yeah, Ryder. Move to the right 4. So x minus 4, I move to the right 4. Minus 2 on the outside, I move down. Okay? So what I put on the board will also be on your notes posted. Okay? This explains all the transformations that can occur. A, H, and K are going to be the same for all 5 of those functions we did today. Okay? All these transformations are going to be the same for any function, even a random graph thrown your way. It's going to be the same thing. Okay? So you could close your Chromebooks. Okay? And we're strictly going to start with quadratics because we've seen those before, and only in vertex form, which is this. This is vertex form. Okay? So quadratic function is a parabola, all right? And your vertex, when it changes left to right, okay, or up or down, your vertex is HK. Your vertex is your H value and your K value, okay? That's how you know what your vertex is. So what are some things that A value tells us to do? If the graph is opening, what direction? Yeah. Good. Opening up or opening down. Then there could be a vertical what? Yeah. Good. Stretch or compression. And if there is a, what's the last thing the A value could do? Reflection over the X. Okay, so A does a lot. Then H indicates an horizontal translation, shifting in what direction? Yeah, Eleanor. Left or right? Good. Okay. And then K indicates a vertical translation, shifting. Yep. Up or down. Good. Okay. What? You're right, girlfriend. So highlight it. Highlight it. That's a good piece of information. Right here summarizes what everything we have on the board. Okay? And if you wrote it in the box above, this explains it a little bit more, breaking up the A especially. Okay? So we're going to try some examples, starting with quadratics. Okay? What I want you to do first is graph the parent function, which is x squared. Okay? And how you know it's a parent function of x squared? Look at the exponent. Okay? So you have on your pink sheet the values for quadratic function. I'm going to teach you a little trick too, remember. Okay. One trick for the quadratic, okay, if you know the vertex and you know your a value is 1, which in this case is your a value 1, your new function, yeah, okay, we'll get to the rest shortly. If you start with your vertex and your a value is 1, we start with, what's the first perfect square number? 1. So we have 1 over 1. If I go back to the vertex, what's my next perfect square number? 4, up 4 and over how many? 2. What would come after 4? 9. So if I go up 9 over 3 in either direction, you have your points. Or you don't even have to calculate them by entering them in. Remember that little trick, and you're all set. Okay? We will be using that more, so you don't have to input numbers. Okay? All right, so we have our parent function. We know our a value is 1. What is my h value? Kaylin. 2, good. And remember, it's opposite of what you see. X minus 2 equals 0. That's how I get the positive 2. Only for the h. What is my k value? Yeah. 4. Okay. What is my vertex? 2, 4. Okay. So that's what plot first. Okay, so the purple, if you can kind of see it, is my new vertex, 2, 4. What types of transformations happen? What is 1? To go from 0, 0 to 2, 4, what happened? Eleanor? In what direction? Right 2, and then up 4. So that's what happened, okay? We moved to the right 4 because we have x minus 2, and we moved up 4 because we have plus 4, okay? So all of these points can move the same way, or you could remember the trick. But if not, if you have your parent function, take this point, move it to the right 2, and up 4. Move this point, right 2, up 4. That's all we're going to see on this graph. Okay? All right. Now number 2. Again, we're going to graph our parent function. And again, you guys will not always have to graph your parent function, just until we get familiar with how the points are. Okay? So here's our parent function. What is my a value? Jeff? Okay. Would it be positive or negative? It's okay. There's a negative in front, so it would be negative 1. Okay? What's my h value? Yeah. 0. What's my k? 3. Therefore, what's my new vertex? 0, 3. Okay, before we graph anything, can anyone tell me the transformations happening? What is 1? Tommy. Up 3. Good. What's another? Yep. Good. A reflection over the x. Okay. So we first start with our vertex, 0, 3. Now, to graph my other 2 points, or 5 points, am I still going up? Should I go up? Like from here, up 1 over? No, right? Why? You're reflected, so instead of up, where am I going? Down. And then if I remember the sequence, okay, because my a value is 1, 1, 1, and then back to the vertex, I go down how much? 4. 1, 2, 3, 4. Over how many? 2 on this side. Okay. So say if you forget that trick, right? Say if you're not sure or not confident in it, what you could do is do your table of values. However, when you do your table of values, you don't have to do -2 to 2. You start with the new vertex in the middle and pick 2 values below, 2 values above. Because all you have to find is 0 and 1, the y values. You will then find 3 and 4. Okay? So if you're not sure of that trick, or if your y value or a value changes, you start with your vertex first. Put in values above. You also know these two. Okay? All right? Yep. Okay? All right. What I want you guys to do, try number 3 on your own. Try number good. What is my k value? Let's see, Nick. -1. An excellent job for that -3. X plus 3, set it equal to 0. It's opposite of what you see. What is the vertex? Eleanor? -3, -1. So what types of transformations have happened? What's 1? Eliza? Yep, go ahead. Down 1. Excellent. Okay, so I'm just going to go ahead and plot my new vertex. Okay, since the a value is 1, I know the trend is still the same. Okay, so how many of you did get a graph like that? Perfect, perfect. Okay, any questions so far on 1, 2, or 3? Yep. Sure. Okay, you start from your vertex. Now, since the a value is 1, there's no additional multiplying, okay? So, since the a value is a 1, think of your first perfect square, it's 1, right? So, up 1 to the right and left, 1. Then you go back to your vertex. Think of your next in line, which is 4. So, you go up 4 and to the right and left 2. That's how you get the additional points. 9 would be next. 9, then 3, and then 16. Yeah, good. Excellent. All right. So now we get to f of x equals 4x squared. And this is where we're going to stop today. Okay. What is my a value? 4. What's my h? 0. Okay. Therefore, vertex 0, 0. What's happening? Just based off the equation. David? Vertical stretch. By 4. Okay? So this is what came up already. Okay? Knowing that my vertex is 0, 0. I'm going to show you with points. Some of you can figure this out. Okay. Here were my parent function points, right? Okay. So when you have a transformation of a vertical stretch and shrink have to happen first. God bless you. Think of PEMDAS. We have two things. A and K both affect the Y values, right? So your multiplication has to happen first. So what that looks like is blue is my new function. My X values are going to stay the same since the vertex is 0, 0. Okay? Now, if I have an A value in front, well, I'm multiplying my Y values original by 4. By 4. So, you take 16, 4, that's 0, 4, and 16. So if there's an A value in front, you're multiplying your original Y values by that number. Okay? Because that stretches out your Y. So this graph, and we can only see these 3 points. Okay? Any questions? All right. Guys, awesome.